Jordan Tigani. Uh, Jordan is the Chief Product Officer at Singlestore, where he oversees the engineering, product, and design teams. So please welcome Jordan with his speech, Keeping Up in a Data-Intensive World with Singlestore. So welcome on stage, Jordan Tigani.
Hi, thanks very much. It's great to be here. Just a little bit of kind of more about my background. I was one of the engineers who helped create Google BigQuery. I guess it's about 11 years ago. I wrote a lot of the storage system. I ended up leading the engineering team for a while, and then leading the product team. So I was with BigQuery for its first 10 years, its first $1 billion or so of revenue, and then about a year ago, I switched over to Singlestore for a couple of reasons. One is because some of the things that they could do and the technology that they had built, it was called MemSQL at the time, but were things that we were trying to do at Google, but we're having a hard time actually building because they're, it can be very difficult, and some of the things that they can do or we can do are people said was impossible. And the other reason I joined was I thought there was actually a big space that was that they were addressing that the other data warehouse vendors, data platform vendors were kind of missing, and that was the sort of handling the data intensive applications. So today I'm going to talk a little bit about what a data intensive application is, why I think that actually data intensity is really the primary difficult concern of a data architecture in this day and age, and I'll talk a little bit about how Singlestore can help. And then just because I'm an engineer, I'll go into a little bit about how it works and how we can how Singlestore can solve these data intensive problems. So just to start out with a short history of modern databases. So I think there was sort of the kind of the first generation was the scale up generation, where you basically had a single instance database, and if you wanted your database to do more, if you had more users, more data, you really had to just sort of buy bigger hardware, and for lots of reasons that this hit scaling limits. But many of the kind of the traditional databases came out of this type of architecture. And in fact, many of the databases that are still in use today really are in sort of the scale up model. Even ones that have distributed versions, they often, the distributed version is really just sort of a handful of the single node versions kind of strung together with some duct tape. Kind of then there was the big data revolution that happened I don't know 10, 15 years ago, and out of that comes, on the analytics side, came Hadoop and MapReduce, and that became just sort of this big sort of juggernaut, because it kind of lets you extend the boundaries of what was possible to do. But it was really kind of a pain in the ass. And then they put a lot of duct tape on top of Hadoop to make it work better. But it had some problems. I think on the application side, the application database side, was the sort of the NoSQL movement, which I see really as an analog to MapReduce, which kind of lets you scale out. You didn't have to buy expensive machines. You could buy a lot of kind of inexpensive hardware, and get your data to scale. But just like MapReduce, there's something you gave up, and you had to, the thing you gave up was kind of your consistency, perhaps, or relational model, or ability to run SQL queries on top of the data. But in exchange, you got a lot of got a lot of benefit. You got the ability to just sort of to go to virtually any size that you want. I think there was a third stage that that came in, I would say 5 or so years ago, where you started seeing, on the analytics side, the data platforms that were sort of, they were taking, they were scale out, and they but they gave you the same sort of interfaces that you had in the traditional data warehouse. They gave you full SQL, but and even better speed than you had in MapReduce. So it was sort of easier to use and better speed. And so Snowflake is the kind of the biggest, I think most well-known example of this, but BigQuery is also a strong example of this kind of analytical system. On the database side, though, I it's been a little bit disappointing as a database person to see that there's kind of no real strong contender has emerged, that did the same sort of thing, that said, hey, you don't have to give up SQL, you don't have to give up consistency, or ACID transactions, or multi-statement transactions, or sort of the hard things that were in databases, that people ended up relying on. And I think one of the reasons that happened is because there was this sort of multiplication of single purpose databases. So you had a time series database, you had a graph database, you had a document database, you had geospatial databases. There were sort of, every use case you had a specialized database. But I think there's also problems to that. And I think the problem to that is you create this extremely complicated data architecture that takes a lot of it. It takes engineers to understand. It has a lot of moving parts, and anybody knows that, like, machines with moving parts, those moving parts can fail, and they can sometimes fail in difficult ways, and it's higher total cost of ownership. And so, I believe that what's coming, and I think that's sort of what I'm going to be talking about, is actually a consolidation where you can take those single purpose databases, and replace them with a single database, and that also can work across database and analytics. And this has sort of been kind of the holy grail of databases for, I don't know, something like 40 years. And it's also something that people said was impossible. The guy who invented Postgres and Vertica, I believe, Michael Stonebreaker, he said, analytics and transactional databases, they're just too different, and they will never be, because the technology necessary to have one versus with the other are too different, that you'll never actually have one that is successful at doing well in both of those cases. I believe that that's actually not true, and I'm going to talk a little bit about, give an architectural example of how it's not true, and also some customer examples of how that's not true as well. So just to kind of set a little bit of like background about what problem we want to solve is, go back to, actually, there's a company that I worked at in, I think it was 2007, before I went to Google. It was a startup company, a little bit ahead of its time. They were one of the first iPhone applications, but they were building kind of this, if you think of Yelp, or restaurant reviews and recommendations, but with a social component. So you can see what your friends are doing and where your friends are eating. And so building out the data architecture for this, you start with a sharded MySQL database is your system of record for your users and entities, and you have all the relational goodies. But there was a lot of kind of semi-structured or unstructured content, in reviews and comments. And so, you use, CouchDB to store these reviews and comments. But the problem about that is that, we also wanted to be able to search over these things, and search, location-based search, and, reasonably complex search. And, to do that, we added Solr. Now, as we're doing this, things are getting more complicated, because the other thing we wanted to do was um, have the search results be impacted by the what your friends are doing. And the fact that these two databases, your users and your reviews are separate from the search index is can make that makes that very difficult. We had to write a lot of specialized code for that. And Solar was basically a precursor of Elastic. And then then finally, we also wanted to do some analytics. And I think one day, we were doing analytics right on the sharded MySQL. Most of you probably know why that's a bad idea. We didn't necessarily know it at the time, but we all of a sudden everything started, stuff ground to a halt, and it turned out that one of our analysts was running some really complicated query over the whole database that was doing a table scan. And so soon we realized we needed a separate place to do analytics. And then of course, when you have all these pieces, and then you want to do something complicated, it ends up being horribly slow. I think our front page ended up at one point was taking like 15 seconds to load. And so you want to add a caching layer. We're using memcached. Redis is sort of the modern version of that. But very difficult data estate here and data architecture, and lots of engineering energy was spent kind of moving between one and the other, and handling consistency and handling updates. It certainly kept a number of us gainfully employed, at least while that company was gainfully employing engineers. Anyway, so I think essentially this was an early version of a data intensive application. And I think that this pattern is something that we see more and more. And so what is a data intensive application? So, I think what we used to call data, big data, was, 10 years ago, that was all the rage. Everybody was talking about, what do you do about big data? I think that was one aspect of data intensity, because sometimes the problem is the fact that your data is just too big to handle it, too big to store. But often that's the data is sometimes the data is moving too fast, and you need real-time information, and but the problems that you hit when the data is moving too fast, or the concurrency is too high, is really the same types of problems as big data. And so there's these other kind of symptoms of something that you see that also really the underlying problem is the intensity of your data. And there's sort of the old parable or whatever of the blind men and the elephant, and each one touches a different part, and they have a totally different opinion of what the actual animal is. And I think that a lot, depending on which direction you come from it, the underlying problem of data intensity looks like something different. There's a great book by Martin Kleppmann about designing data intensive applications, and he does talk about, it's a lot about architecture and how to tie these different architectural pieces together. These kind of applications are everywhere. And if you think about, just a lot of the interesting applications, like, if you do search on Google, well, that's really a data intensive type of application. You're not really going to use, if you just think about what kind of data stores you'd use for that, you're not really going to use a data warehouse for that, even though it's sort of an analytical style query, because you need to be able to do, hundreds of thousands of these or millions per second. Uber congestion pricing is kind of an example of, actually the Uber app is a very data intensive application. There's just lots of different data points that are moving around. You're not going to use a data warehouse. You're not going to use, you can't, just MySQL is not going to cut it for understanding congestion pricing. I think it's one of the, things about it is it's, you want to make decisions based on decisions within an application based on data um, that is happening outside of just the current the current user or the current context. Who else is booking rides on Uber, for example, is going to impact your cost to get a ride. Um, Leaderboards are also a kind of a key example. A leaderboard is really, to compute a leaderboard, it's an analytical query, but again, you're not likely going to use your data warehouse for that type of analytical query in your application. you know Other examples, things are what's trending on Twitter, if you want to have complex portfolio management, et cetera. These are all other examples of data intensive applications. So, what characterizes a data intensive application? I mentioned that sort of big data was kind of an indicator. So sometimes it is that you just have a lot of data. Sometimes it's the data is changing quickly. The data is coming in. So it's not just that it's being ingested quickly, but also that it's changing quickly. So sometimes if things are being updated quickly, that can be a sign that that your application is data intensive. Also, latency requirements. So if you have, if you want to show something to your end users, like when I mentioned the homepages of the website that I worked on, took 15 seconds to load. Like that's just not acceptable in this day and age, that somebody goes to a website and it takes 15 seconds to load. If that happens, they'll just leave. And I think there's been a bunch of studies that have been done, say basically every 100 milliseconds, you lose a certain percentage of your users. And so if you want to do something that looks like an analytics, but you want to show it to your users, then often the data stores that are designed for analytics are not going to be sufficient. High complexity also can be a driver, and high concurrency. If you have hundreds of thousands or millions of users accessing simultaneously, then you may need a different type of data store to handle that. So just to drill down on some of these things, you kind of want data to be ingested quickly. You want changes to be reflected immediately. So if you have that leaderboard example in Angry Birds, and you get the high score, and then you go to the leaderboard, you want to see that you are the one that is in the high position. So kind of if you have, if you're synchronizing multiple databases and that synchronization gets behind, then users get upset. I mentioned that kind of, every 100 milliseconds, you lose some sort of user attention. And then just, users don't come kind of in a, laminar flow across the day. They tend to all come at the same time. Things start happening, things start ramping up, and then you need to be able to scale to high concurrency when you go viral, or when something happens, or when everybody comes to the site. When Facebook is down, everybody may come to your site instead of Facebook. Sorry for the dig, but anyway, so traditional solutions tend to not work for these things. Like, so for data warehouse, fast ingestion, particularly fast updates, are hard, because just column stores. The whole reason that column stores work is because you take a large amount of data and you can sort of compress across the columns, and you can write those kind of all out in one go. If you're trying to update a single entity at a time, then basically you're not going to get any benefit of a column store. And then on the transactional side, you end up having to, traditional databases would end up having to, sacrifice, some sort of, consistency in order to scale in a lot of these cases. And then on the low latency side, I worked on a data warehouse where, we were, the key point was throughput. You wanted to get as much work done over time as possible. But at one point, a couple hundred milliseconds was not considered a blocker. It was like, we were letting you do things that used to take hours and do those in minutes or seconds, but milliseconds was not something that people were really concerned about. And then on the transactional side, if you want to do an analytical style query, you just, the databases tend to just not be set up for that. Like, if you want to do something that looks across the breadth of data to see, like, in the Uber case, to see what else is going on in the world, then who else is requesting rides, because that's going to affect your cost. That's a difficult type of query for a transactional database to do. And then data warehouses, they can scale out, but they're really not designed for high concurrency. And on the transactional side, if you run the analytical queries use a lot of resources, and if you want to run a lot of those at the same time, then that's going to your database is going to fall over. So I sort of building up to this, but Singlestore is a database designed to be able to handle these types of applications, to be able to handle those in a single database. And here's just an example of a couple of our customers that are using it for their data intensive applications. So what is Singlestore? It's a database that can work across transactional and analytical use cases. And so traditionally we've called it HTAP, the hybrid transactional and analytical. But the workloads that are true HTAP are actually pretty niche. But it turns out that we can go pretty far on either side. So we can actually do large scale data warehousing analytics. And it's what can be interesting. It can be interesting when you come at it from either side. If you come at it from the analytics side, HTAP ends up looking like, faster analytics, fast dashboards, low latency, real time analytics. So, a lot of IoT use cases, for example. And those are super interesting and they can be very important. But there's also some really interesting applications that come from the other side, that come from the transactional side, where you have a transactional workload that that has some aspects of analytics. So you need, the leaderboards example is a good thing. And I think a lot of so coming from the right-hand side where people can do faster analytics, I mean, that's sort of the direction that the data warehouse vendors are trying to go. And, I think they it's difficult. And so it's taking them a while to get there, but sort of coming from the other side is a big open space, because I don't think there's very good options for a database that can do they can add analytics to your application. And sometimes that could be, the reasons you could do that, you want to do that could be, embedded analytics, you want to show dashboards, you want to show, charts to your users, or, other things like, surge pricing or trending on Twitter. So, just Singlestore is, we have, it runs everywhere. It's a managed database, managed cloud service, cloud managed service in AWS, Azure, GCP, Red Hat OpenShift. It runs in, there's a containerized version if you want to deploy it as containers. You can run it on-prem. You can run it in self-hosted in the cloud. We're very good at ingesting data, ingest from Spark, from Kafka, and then you can do your dashboarding and your analytics on top of it. But then you can also build your applications on it. So kind of this idea of having one database in one place where you can do your both your application and your analytics actually works in Singlestore. So I kind of was talking about an older version of a data intensive application that that had a number of different databases, but just to show kind of how this would work in a more modern example, and this is ends up being quite common, is you have your application is using Postgres, and it's doing batch ingestion and storing data, everything's working fine. Perhaps you needed need to shard it to handle the scale, but in general that, you can handle that, but then you want to integrate some third-party data. And so you throw in Mongo. Okay, so the data synchronization starts getting a little bit complicated, and then it all starts slowing down. So you add Redis to as a cache. But then you want to add search. You want to add be able to search over history, and so you add Elasticsearch. And then you throw in some clickstream data coming from your IoT sources or other sources, and then you have Kafka in the mix, and then everything these days you want to do AI and ML, so you add Spark, and next thing you know, like there's all of these arrows going everywhere, and all of these things that they can break, B, that require somebody that deeply understands these things, and C, ends up it's going to sort of cost you money. Oh, and then finally you want to do your analytics, and so you use snowflakes for your analytics. So the single store version of this is your application runs against Singlestore. You can add your IoT sources, you can add your batch sources, your operational sources, your third-party sources, connect your AI ML through Spark, and much simpler data estate. So what is it that makes Singlestore tick? So the one, I was a storage guy, so I worked on the BigQuery storage system. I led the BigQuery storage team, and for my money, in my opinion, the big differences between databases are how they store their data, and Singlestore has some pretty amazing storage technology, and I'm going to talk a little bit about how the storage technology enables us to do some of the things that we do. Another kind of really cool thing though is that Singlestore has a lot of cloud native features, separation of storage and compute, which is sort of table stakes on the cloud these days, but is also pretty rare for something that you can run on-prem as well. So taking some of these things that are cloud native, unlimited point in time restore, where you can basically get back to your database at any time in the past, and being able to do that wherever you are. It's a little bit like think of your phone, which uploads your photos to the cloud, and being able to sort of get those, and just that to happen seamlessly, so that's another thing. Also, just the flexible pay-as-you-go spending model is something that tends to be cloud only. And then lastly, sort of this all of your workloads in one database. Singlestore can do transactions. It can do document store. It can semi-structured with JSON types. It can do geospatial time series and full text search as well in one database. Okay, so now I'm going to dig into how this works under the hood. There was a couple of months ago, one of the Singlestore engineers got in a kind of a fight with somebody, or a friendly argument with somebody on Hacker News, and the person basically said that what we were doing wasn't possible. Everybody knows it's not possible, that you either have to optimize your database for one thing or the other. And so I kind of want to just show how it works, and or just enough of how it works to basically just say that, hey, this is possible. We did it this way, and you could do it too. So the thing we started out with was, the original name of Singlestore was MemSQL, and we had this fast transactional in-memory database. So it's in-memory row store. We replicated it to multiple machines, so it would be high availability, even though it was in memory. Partitions were striped across machines so that we could scale out. And then we added a lock-free skip list index. So basically, this is how you can figure out what data is where. And this using lock-free data structures lets you basically have very high concurrency, because you never have to you never have to do table locks. You don't have to do, you don't have to do row locks. So you can do lots of stuff at once, and then you could do incredibly fast lookups. I mean, it's an in-memory database, very, very fast. Most of the initial MemSQL engineers were world-class programming competition winners, and they built a pretty extraordinary fast in-memory database. Now, of course, if you're in memory, you want to make sure that you can also, it's persistent. If all of those machines crash, that you can recover the data. In general, in databases, the way you do that is the transaction log. So we take advantage of SSDs, which are higher concurrency and lower latency than kind of traditional spinning disk architectures. And so we use local SSD to write a transaction log. We append data to the transaction log, which is very fast. And so you can do this at in single-digit milliseconds. But the other nice thing about it is it doesn't slow down reads at all. So the SSD, this transaction log, only gets read if you need to recover. And it's just a simple write in the case of an insert or update in the database. And then the way we also this is I think the clever part, which is in order to add analytics to this, we basically have a column store that's stored on disk. And so what happens is the row store periodically gets written out from memory to the column store on SSD. And so that when you run analytical queries, analytical queries generally are much faster to serve from a column store than a row store. And because you usually only access a subset of columns, then you can compress across a column store much better. Column stores just tend to be much better for analytics. But the problem with column stores, and the reason that they don't work as well for transactions, is because as I mentioned before, they get their benefit from being able to write out big chunks at once. So we take the row store and then we write those out periodically, so we can write big chunks of column store. And then when you run the analytics query, so it's not just a version that's behind a bit, because we run the query, we'll merge in the results from the row store and the column store, so you get a consistent ACID transactional view of your data. And this also allows us to scale at sizes larger than memory, because we can, if you have more, disk tends to be larger than memory, and so if you write more data out to the column store, then you have memory. You basically just treat the memory as a cache. That also means in order to do transactional lookups, you have to be able to find something quickly in a column store, which is the other reason that column stores don't usually work well for transactions. But we have a seekable column store with a column store index. So basically, we can jump right to the location where the data is without having to read a full segment. And then finally, we added a third tier, and the third tier is object storage. And so object storage, you can think of as S3, GCS, Azure Blob Storage, or Ceph or Cohesity if you're running on-prem. And so Blob Storage basically, it lets us kind of just have virtually unlimited data sizes. And so it's also asynchronous. So I think one of the cool things we've done is we added SSDs without really slowing down this really fast in-memory database. And now we're adding object store without slowing down this, without slowing it down either, because the blobs here can be written out asynchronously, and then that allow you to have multiple readers. And this is one of the cool things is you can mount the same single store database in multiple locations. So you could have your transactional workload that runs, and then it's generating your data, and it's your system of record. And then you can basically have another compute cluster that mounts that database as read-only, and you can do your analytics. Because remember, I mentioned in the Pelago case where we had the analysts wanted to access the data, but it slowed down our compute cluster to run the analytics queries. You can actually have those be completely isolated environments. And then also we have the transaction log gets written. So we have the full transaction log, which allows you to do point in time restore. I won't go too much into this, but this is sort of like how it would work if you were to do it. This is how we can do an insert in in sub millisecond. Basically all we have to do at the time is update memory and append to the tail of a transaction log. And also, if data is hot, if data is in memory, we can do significantly sub millisecond lookups via our skip list and our row store. And then if the data is not in memory, we can use our on disk column store or column index and the seekable column store. Then we populate it into the row store so that often you get locality of reference. And if someone asks for a key or if someone asks for something in a range of keys, they tend to ask for that same thing again. And the analytics query, we have column statistics in memory so that we can do segment elimination, a lot of sort of fancy stuff. So we have to read the minimal amount of data, and then it's just a standard analytics query. Okay, so then Singlestore in the real world, it's not just something that kind of looks nice in slides. We have a lot of big big logos, big companies that are using us for real world things. Uber is using us for their surge pricing, as well as marketing segmentation, etc. And then just some examples of how we can real metrics. So Akamai wanted to make sure that we could handle their load, so they benchmarked us at 10 million upserts per second. So appends are generally pretty easy to do because you just you write to a log, or you just write. A lot of systems can do fast appends, but this is upserts, updates are very hard to do at this kind of speed. Uber uses us, and they have a 2 millisecond SLA. So like they need to get a result back in 2 milliseconds. And that's a transactional case where they need to look up the user segmentation. But Bank of America has a 50 millisecond SLA, and that's an analytic query to basically say, is this transaction going to be fraud? And then on the concurrency side, we can do hundreds of thousands of queries per second. And I also showed at the beginning that you have a very complicated data architecture, and then people are replacing multiple databases. We see a lot of patterns that people are like, well, they start with MySQL, and then they realize that hey, I can do my full text queries in here, so they don't need Elastic, and then they realize they don't need Redis because it's fast enough on its own. So a number of times we see companies that replace multiple different data stores to a single one. And I want to go into a little bit of just depth on one of these, which is Fathom Analytics. Jack Ellis, who's the founder, he wrote this blog post in March about building the world's fastest website analytics. So they do kind of a privacy safe version of Google Analytics, and so they have their pixel on millions of pages, and so they have a lot of data coming in, and a lot of data coming in very fast. And they moved that data to Singlestore in March, and you can see as at the first line, as we moved our analytics data to the database of our dreams. Then in August, they optimized Singlestore. They also realized they could get rid of Redis. They had a Redis cache, and they didn't need that anymore. And then just a few days ago, he posted and said, this is why we ditched DynamoDB. It's like, hey, we're using DynamoDB. We loved it. We thought it was going to be great, but it turns out we didn't need it. We just used Singlestore. So in summary, I think data intensity and data intensive applications are a big, broad category that's underserved by the data storage and the data analytics tools out there. And Singlestore is a great way to tackle them. I also also talked a little bit about how you could build something um, that would be able to handle your data intensive applications in one package. And hopefully I convinced you, or at least piqued your interest that Singlestore does work for these cases in the real world. You can try it for free of our managed service, singlestore.com. And that's it. Thank you very much. I think we have a couple minutes left. I'm happy to answer any questions if people have them.
Thank you very much, Jordan. Indeed, we have a few questions.
Great.
So we can use the remaining minutes to answer those questions. Let's see. The first one could be a simple one. Is Singlestore open source?
No, it's not open source.
Yeah, okay.
It's not open source, but it is free to use. We have a free tier in our downloadable version. You can install Singlestore. You can run it on up to 4 nodes entirely for free.
Mm-hmm. This was the most popular question, by the way. So the next one. Are Oracle DB2 SQL Server not a modern traditional RDBMS sys?
Sometimes these are sort of fighting words when you say, no, you're not modern, but I don't think they are. I think, in 15 years ago, Michael Stonebreaker said, the database world is ready for an architectural rewrite. And these DB2, Oracle, SQL Server are all really built on top of kind of an old school architecture that was designed around, the primary performance characteristic was the spinning disk. So like the data structure they used was a B tree. B trees are great for disks, and like having, all this stuff to get the file system out of the way, all this energy, all this work that they did. And they're really still single box. They're really still scale up, and they don't scale out particularly well. So I would say no, they're not modern databases. They tend to work, super well for some use cases, but they don't have the same scaling characteristics, and they don't have the same kind of just flexibility that you see in a more modern architecture.
Thank you, Jordan. And last question so far. Are geospatial queries supported?
Yes, geospatial queries are supported. We have geography types. So sometimes some people use geometry or geography based on whether you use, I think, spherical or ellipsoid based math. But I think we do the more complicated one. I think is the geography query support.
Oh, and we got a few questions, 3 more.
Great.
Let's see. Could you compare with Green Plum?
Yeah, I think that Green Plum is a little bit more of a legacy architecture. I don't know quite as much about Green Plum, but I do know that we have helped people migrate off of Green Plum as they modernize their their analytics.
Okay. Then the next question, what is recommended way of creating analytical workflows?
So analytical workloads, I think they just work in Singlestore, and we have, I think a lot of our, customers are using it for fast dashboards and for fast, real-time analytics. We also see, we see a lot of people using it to augment their analytics. So, somebody who has a Snowflake or has Teradata or has another analytical database or data warehouse, often those things have they hit the wall in some workloads. You may need a dashboard that has to run 500 queries at once, or you might have something where you really need to have interactive low latency. And so we see people using Singlestore, and they'll either write to both places, or they'll write to Singlestore and then use Singlestore to batch up the writes and then flush those back to the other database. We see that actually pretty commonly with Snowflake.
Okay, then the last question again. Hi Jordan, what are you using for automating versioning the schema setup, like DBT, data build tool, or similar?
That's a great question, and we are working on a DBT connector and DBT integration, because I think that I think that's really awesome technology. I think DBT is very cool, and just one other thing though is that Singlestore is MySQL wire compatible. So tools that work with MySQL will work with Singlestore. So a lot of the times there won't be a specialized Singlestore connector, but there will be a MySQL or MariaDB connector, and those will work just out of the box.
Okay, thank you, Jordan. So there are no more questions.